Hi everyone, and welcome again to Nettle, the go-to place to learn about business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a quite underappreciated yet very powerful and intuitive model for financial time series, that is the autoregressive conditional kurtosis model, which is a generalization and an extension of generalized autoregressive conditional heteroscedasticity models, or GARCH models, that have been pioneered by Engel and Granger and later by Boleslav. And well, we have got a full playlist on different specifications and varieties of GARCH models, so check these out if you're interested in GARCH itself, not in the generalizations of GARCH. However, the autoregressive conditional kurtosis model goes one step further than your regular GARCH, and it has been developed by Brooks et al. In 2005 in their paper in Journal of Financial Econometrics. And the logic is that when you are dealing with GARCH, the autoregressive process specifies the volatility or the variance of your financial time series, for example, your returns. However, why not also use an autoregressive process to describe or explain, perhaps better than the baseline model, the propensity of the return generating process to generate extreme tail events, to explain the heavy-tailedness of the distribution. And well, the go-to metric for heavy-tailedness or extreme events likelihood that occur in a particular distribution is kurtosis. So what Brooks et al. Proposed is to combine the GARCH equation for the volatility or for the variance. That's quite a common parameterization. You've got your conditional variance in time t explained by unconditional variance omega. Then you've got immediate disturbance, which is the squared error term, the residual term in prior day t minus 1 multiplied by the immediate persistence parameter alpha, as well as by the conditional variance persistence itself, described by the persistence parameter beta, multiplied by the conditional variance in time t minus 1, so in the previous observation, in the previous day, most commonly. However, they also, by analogy, by extension, proposed the same equation, or at least a very similar equation, for kurtosis in time t, kt. You've got unconditional kurtosis omega, you've got lagged conditional kurtosis kt minus 1, and parameters beta and alpha. However, what is different here, and that's due to the scale of the kurtosis parameter, is the formula for the immediate disturbance. Here it is lagged residual e t minus 1 to the fourth power divided by squared lagged conditional variance. And this is due to the fact that the kurtosis formula deals with fourth central moments. And this is why this is to the power of 4. And because kurtosis is scale-free, we need to scale it by dividing it by the squared variance, essentially. However, how one can estimate this particular processes using maximum likelihood? For variance, it has been quite standard to just express your variance as a scale parameter that then is plugged into a probability density function, and then you use maximum likelihood there. However, for kurtosis, it's not always simple or even possible mathematically to express kurtosis as a function of your distribution parameters. However, this is where the student t-distribution comes into the picture due to its flexibility and relative computational simplicity. Student's t-distribution, and particularly its flexibility in terms of shape, the shape parameter for the student's t-distribution is the degrees of freedom, denoted here as mu. It allows you to proxy very fat tail distribution if the degrees of freedom parameter is very low, and distributions that are essentially normal when the degrees of freedom parameter is very high or tends to infinity. What Brooks et al. Used is a very neat relationship between kurtosis and the degrees of freedom parameter in the student's t distribution. You can express quite simply and in a closed form solution, which is very essential for the computational power or computational implementability of the model. You can express the degrees of freedom parameter mu as a function of kurtosis at a particular time, and that solves all of it. You can simply calculate the degrees of freedom parameter based on your kurtosis, which is given by this autoregressive function. Then you can retrieve the scale parameter lambda using both the conditional variance and the degrees of freedom parameter in this very time, and then plug it all into the probability density function, and that basically propels your maximum likelihood estimation further. So let's implement the autoregressive conditional kurtosis model in Excel and compare its results and its explanatory power to standard GARCH, and also discuss some basic statistical hypothesis testing associated with autoregressive kurtosis phenomena or processes. Here we have got Bitcoin returns, just to spice it up. We've got 2 years worth of Bitcoin price data, and we can calculate log returns by calculating logarithms of the ratios of consecutive prices. That allows us to calculate it for the whole sample. Then, as our baseline specification, let's use the method of moments, which is the most straightforward and computationally non-intensive way. As our baseline location parameter, we can just use the average of our returns. Again, as those are log returns, we can use simple arithmetic average without any reservation. As our baseline unconditional variance, will just input the sample variance, because the baseline specification assumes that there are no persistence effects, so alpha and beta are equal to 0. For kurtosis, we just calculate the sample kurtosis, and here is something that you need to be aware of. These specifications, these autoregressive functions, as well as this particular relationship between degrees of freedom and kurtosis, uses not the excess kurtosis that Excel gives you, but rather just the normal kurtosis. So if you're using the kurt function here, you need to add 3 to keep it all on the same level playing field. And just as with variance, we assume that there are no autoregressive kurtosis processes in the baseline specification, so alpha and beta here are 0 for kurtosis as well. And then to keep track of whether the process is stable, just as in regular GARCH, this generalizes here quite well, we need just to add alpha and beta parameters, and then we'll demand of our optimization algorithm that those sums are less than 1 in our maximum likelihood optimization. But first of all, let's calculate our day-to-day residuals, subtracting our location parameter mu from our log returns throughout the full sample. Then we can start calculating our starting values for variance and kurtosis. So for the variance, it's omega divided by 1 minus alpha minus beta. And for the kurtosis, as an extension, it's our starting kurtosis divided by 1 minus alpha minus beta for the kurtosis autoregressive process. And obviously here, as those are zeros, they're just equal to the values of the sample variance and kurtosis. That's something that we expect to see. The volatility is just the square root of the conditional variance. And then we'll need to express our distribution parameters based on our moments. And here we're also using the method of moments. So for the shape parameter, we need to implement this particular relationship. So 2 times kurtosis minus 3 divided by kurtosis minus 3, which gives us the shape parameter originally at 6.71 approximately. And for the scale parameter, we use the square root. This is raised to the power of a half, so square root of, in the numerator we are having our conditional variance ht times the degrees of freedom parameter minus 2 divided by the degrees of freedom parameter mu t. And that gives us the scale parameter of 3.2%. And here we already see some quite relevant restrictions that the model implicitly demands of both the scale and the shape parameter. Most notably, for the kurtosis to exist, our degrees of freedom parameter needs to be higher than 4. If it's equal to 4, kurtosis is infinite. If it's less than 4, kurtosis does not exist. We need to keep that in mind. And all the more so, if the degrees of freedom parameter is less than 2, then variance does not exist. The process is infinite variance, essentially. The variance is even undefined if it's exactly less than 2, and infinite if it's equal to 2. However, the more restrictive condition is that the degrees of freedom needs to be higher than 4 for autoregressive kurtosis to be even meaningful, because if the distribution is so heavy-tailed that kurtosis is infinite or undefined, autoregressive kurtosis does not make sense as a concept. Keeping that in mind, we can calculate our density for our log likelihood implementation. So here, to calculate the density, we first need to implement the gamma function. This capital gamma is for the gamma function, which is a generalization of the factorial. Here we input the shape parameter, the degrees of freedom, nu plus 1 divided by 2. Then in the denominator, we're having the scale parameter lambda times the square root of the degrees of freedom parameter nu again times pi. Pi is just a function without any arguments in Excel as usual. And then we times it by gamma function of our shape parameter nu divided by 2, the degrees of freedom divided by 2, essentially. That deals with the first fraction, and then we are only left with this particular expression in brackets, which is 1 plus 1 over the shape parameter, the degrees of freedom, times the square of scaled residual. So we input our residual here, which is x minus mu, we have already calculated that, divided by the scale parameter, which is lambda squared. And then we close the parentheses, and the final thing that we need to implement is raise it all to the power of minus degrees of freedom parameter mu plus 1 divided by 2. And that gives us the value of the probability density function at the first point. For our log likelihood purposes, we can simply calculate the natural logarithm of this straight away, and also to enable faster and seamless convergence of our optimization algorithm, we'll implement a penalty function, which is basically an if-error function. If we cannot calculate the natural logarithm, if there is an error, for example, if the function returns divided by 0, something like that, something that we do not want our algorithm to do, we just input a very large negative number so that it's a penalty function and the algorithm knows that it shouldn't venture in this direction. So let's return negative 1000, for example. And here we can already input most of our formulas throughout the sample. However, the thing that we don't need to forget is the autoregressive functions here. The very first variance and kurtosis are inputted using the long-term values as per the parameters we work here. However, from day 2 onwards, we use the autoregressive equation. So for variance, we do omega, and that needs to be locked row-wise, plus alpha, which is again needs to be locked row-wise, times our residual, and we'll lock it column-wise so that we can also implement the same formula for kurtosis without much manual work, squared. And then we add our beta parameter for variance, again, log the row here, times the lagged conditional variance, which is just the immediately cell one higher. And that, again, you might have guessed, due to alpha and beta being 0, it still equals sample variance. That's exactly what we wanted. Then we drag it across, and for the kurtosis, we need to change this function to enable a different immediate persistence function. So here we'll raise our residual to the power of 4 and divide by lag conditional variance squared. And that ensures that kurtosis is scale free. This particular parameterization has been proposed by Brooks et al., and it is more natural, more theoretically grounded when you're dealing with kurtosis, which is again a scale-free moment. And then finally, we can drag these functions down and then drag everything throughout the whole sample. And that allows us to calculate log likelihood, which is the sum of the natural logarithms of our probability density functions. This gives us a log likelihood of 1376 approximately, which we'll copy over here to keep track of how much of an improvement does our model reach if we allow some other parameters to vary. And that is the center point of our likelihood ratio test that we'll use as a test for first of all GARCH effects and then autoregressive conditional kurtosis effects. So now let's go to solver and specify our task. We need our log likelihood to be maximized, and we need to change, first of all, parameters that are associated with standard GARCH. So our location parameter, mu, as well as our variance parameters, omega, alpha, and beta for the variance process. We might want to untick this particular cell because some of our parameters, most notably location, can be negative, and we can stick with the gradient descent algorithm. Now we click solve and wait for the algorithm to converge, which should not take too long. And the algorithm has just converged to the optimal value. We can see that the log likelihood has improved to 1389. We can copy that and paste it here as values and calculate the chi-squared statistic, which is 2 times the improvement in the log likelihood value as compared to the previous specification. To test for the significance of GARCH effects, we can use the right-tailed chi-squared distribution, inputting our chi-squared stat and number of the degrees of freedom, which is equal to the number of additional parameters our model included. And here, the additional parameters that we allow to vary are alpha and beta. So we've got 2 parameters, 2 degrees of freedom, and that gives us a p-value which is essentially 0, meaning that GARCH effects are essential in explaining the dynamics of Bitcoin returns and Bitcoin volatility. However, what about conditional kurtosis effects? Well, this specification would be very easy to achieve. We'll need just to change the cells that we want enabled as our arguments, as variables that we allow to change to achieve maximum likelihood. So here, instead of just the variance related parameters, we are including the kurtosis related parameters. And just to make sure that the process does not explode, we can add a constraint that these particular sums of parameters are less than or equal to 0.99. Again, they should be less than 1. However, Excel's solver does not allow for strict inequalities in constraints, so we just go for the next best thing, less than or equal to 0.99. And then we stick with gradient descent, click solve, and wait for the process to converge. And we can see that the process has converged to an optimal value, with our log likelihood now equaling 1393. We can copy this value over here, and as we still have got 2 additional parameters, kurtosis alpha and kurtosis beta, we can drag these across to test for statistical significance of our results. And we can see that while autoregressive kurtosis phenomena are less economically impactful than autoregressive heteroscedasticity phenomena, they are still statistically significant at 5%, with a chi-squared stat of 7.24 and a p-value which is less than 5%. To see how kurtosis evolves through time according to our autoregressive equation, we can just plot a quick line chart over here and watch quite naturally how there are spikes in kurtosis, in the heavy-tailed nature of Bitcoin returns across time that are associated with well, spikes in volatility, new information being released on the market, panics or irrational exuberance by investors. You can explain these things conceptually in a number of ways, but what we actually care about here is that this dynamic of autoregressive kurtosis and the impact it has on the fatness of tails of the distribution adds a meaningful layer of explanatory power to our GARCH models. And that's all there is for the autoregressive conditional kurtosis models of Brooks et al. And its implementation in Excel. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.